In this video, we're going to cover the last topic in numerical integration that we want to cover this year. So we've already covered the rectangle method, the trapezoidal rule, Simpson's rules, and we also covered the Gauss quadrature for evaluating the area under the curve. The one method that we would like to talk about is Richardson extrapolation. And Richardson extrapolation is a general method to find using two estimates to find another estimate using extrapolation, as we will present it in a minute. When we take that Richardson extrapolation and we apply it to the a trapezoid rule, we are then using what we call the Romberg's method. So Romberg's method is using Richardson extrapolation and applying it to the trapezoid rule. So basically, the Romberg's method is, you can think of it as an extension to the trapezoid rule, where we are going to use we're going to use the estimation of the numerical estimation of the area under the curve using the trapezoid rule, and we're going to use a few of them to find a very good approximation for the area under the curve. So Richardson extrapolation is as follows. Let's say I have a quantity A, and this quantity A can be approximated by a numerical algorithm when I choose a step that's equal to h1. The difference between the true value and the approximate value is equal to a constant multiplied by the step to the power k1 plus maybe another constant or an error term that's directly proportional to the step size to the power of k2. Now, if we repeat using a different step size, let's say h2, then a, which is the true value, is equal to the approximate value, which is function of h2, plus a constant multiplied by h2 to the power of k1. You can see this term is exactly this term, but with a different h, plus an error term directly proportional to h2 to the power of k2. Now, if we multiply this by, if we multiply the second equation by t, which is the ratios of the h's, multiplied by k1, and if we then take these two equations and subtract them from each other, we will be able to get an estimation for A that has an error term that is directly proportional to h1 to the power of k2. So this is a little bit abstract. We're going to now show it in the trapezoid rule just to explain to you. So let's recall the trapezoid rule. The trapezoid rule is a method to find the area under the curve by simply, for every interval, so we divide the whole integration domain into subintervals, and for every interval we draw a trapezoid and calculate the area of that trapezoid for that interval. By summing the area of those trapezoids, we get an estimate for the area under the curve. We also would like to recall that the error in the trapezoid rule is directly proportional to h squared. So let's try and understand how we can use that information. Let's assume that I choose a particular h, which is the width of the interval. The true value of the integration is equal to the numerical approximation, which is we are using I sub t for that, as a function of a step size h, knowing the math behind the trapezoidal rule, we can write the error term as follows: that the difference between I of h and I sub t of h, the difference is equal to a constant multiplied by h squared plus an error term that is a function of h power 4, or an error term that's directly proportional to h power 4. Now, if we repeat this with half the step size, so we make our intervals have a width of h over 2, then we can say that I, which is the true value when I use h over 2, is equal to the numerical approximation using the trapezoid rule when the width is equal to h over 2, plus a constant multiplied by h squared over 2 squared, plus an error term directly proportional to h power 4 divided by 2 power 4. Now, I'd like to get rid of this constant c. So to be able to get rid of this constant c, I will multiply the second equation by 4 and then subtract the first and the second equation. So first we multiply the second equation by 4. You can see here 4i is equal to 4i sub t plus c multiplied by h squared. And then I can subtract. Remember that I is the true value and it is the approximate value. Knowing that, I can then estimate I, which is the true value, to be equal to 4 multiplied by I sub t when I use half the step size, minus the trapezoidal, the approximation using the trapezoid rule with the width of h divided by 4 minus 1, plus an error term that is directly proportional to h power 4. So really, what we did here is knowing two estimates for I, and we know that these two estimates are the error term is directly proportional to h squared. We used those two estimates and did some sort of calculation, and now the result is actually the error term in the result is directly proportional to h power 4, which means that we used two values that are h power 2 to get an approximation that is way more accurate, that the error term is actually directly proportional to h power 4 rather than h power 2, which means it has higher. Now let's say that you done this Richardson extrapolation once, and now you've got some estimates that are directly proportional to h power 4, which means that the true value, which you're aiming to find, is equal to the numerical value that was obtained with a step size of h. The error is equal to a constant multiplied by h power 4 plus an error term that is directly proportional to h power 6. Now this is a property of the trapezoid rule, is that you're missing the error term that is h power 5, and so every time you actually do this using the trapezoid rule, you're going to get error terms that are h power 6 and then h power 8 and then h power 10, only the even numbers. All right, so we repeat this using half the step size. Repeating this with half the step size implies that true value is equal to the numerical approximation using the trapezoid rule with h over 2 as the step size, plus a constant multiplied by h power 4 divided by 2 power 4, plus an error term that's directly proportional to h power 6. Getting rid of the denominator here by multiplying by 2 power 4, we will get this equation. Then subtracting as well, just similar to what we did before, then we'll get an approximation using this term, which is 16 multiplied by the value obtained with for h over 2 minus the approximation obtained with h divided by 16 minus 1, and the error term is directly proportional to h power 6. Again, let's say you did this, and then you have now an error term, or you have an approximation whose error terms are directly proportional to c h power 6 plus another error term that is directly proportional to h power 8. Repeating with h over 2 will give an error term that's directly proportional to h power 6 divided by 2 power 6 plus an error term directly proportional to h power 8. Getting rid of this 2 power 6 by multiplying this second equation by 2 power 6 will give this equation 2 power 6 is equal to 64. Again, subtracting, we get an estimate for the true value using this equation, and the error term is is directly proportional to h power 8. All right, so how would we implement this method? This method is usually implemented using the table that you see on the slide. K is called the depth of the table. When k is equal to 1, the approximations are directly proportional to h squared, or sorry, the error in the approximation are directly proportional to h squared. K equal 2, the approximations are, the error term in the approximations are directly proportional to h power 4. 3, the error terms are directly proportional to h power 6, 4 are O h power 8, and 5 are O h power 10, and so on. J, where j goes 1, 2, 3, 4, and so on, gives implies the width of the intervals used in the trapezoidal rule. When j is equal 1, that's the first choice for the width of the trapezoid. When h is equal to, that means the width of the initial width of the trapezoid or of the interval is divided by 2. J is equal to 3 means h is divided by 4. When j is equal to 4, the width is divided by 8, and so on. So you start with h over 2, h over 4, h over 8, h over 16, and so on. So you divide you divide the previous choice by 2 every time as you go down in the table. Using the previous equations that we developed for obtaining a better approximation using extrapolation, the term here is obtained by multiplying 4 by this term minus this term, where this term is this term and I11 is this term, divided by 3. In the next cell in the table, we have I22, where 2 is j, the first subscript is refers to j, and the second subscript refers to k. So I22 can be obtained by multiplying this value by 4, subtracting this value, and divided by 3, and so on. And so we can fill those cells in the table. To obtain the next value in the table here, we take this value multiplied by 16 minus this value divided by 15. And to fill this table, the same thing, take this value multiplied by 16 and subtracting this value and divide by 15, and so on. To obtain this approximation, we take this value multiplied by 64 minus this value divided by 63, and so on. And you could see the table is filled in that manner. A general expression for any cell in this table, I subscript j comma k, can be obtained by using this expression, 2 to the power 2k minus 1 multiplied by the expression at cell j plus 1 k minus 1 minus the expression at cell j comma k minus 1 divided by 2 power 2k minus 1 minus 1, and the error term is h1 to the power 2k. Usually we decide on stopping when the term I sub 1k and I sub 1k minus 1 are very close to each other, or the relative error is less than a particular stopping criteria. So basically, once, for example, when we start here and then fill this table in this manner, and then we compare this value with this value and see are they close enough or not. If they're not close enough, then we continue table this way, and then we compare this value to this value and see are they close enough or not. If not, we continue and so on, as we will see in the next examples. So here we have, we're going to follow the examples that we presented before. We're trying to find the area under the curve for the function e power x on the interval from a equals 0 to b equal 2. And just as a reminder, when we did this using the trapezoid rule with 71 trapezoids, we got this number. And at that time, the absolute error was that value, 0.000042. Now we'd like to use this new method, which is the Romberg's method, applying the Richardson extrapolation to the trapezoid rule. We need to find the depth k, starting from the first h as the whole interval. And we'd like to see what the estimate for this, for the same integral, we'd like to find k such that the estimate for the same integral has the same or less absolute error, which is the error obtained when we got 71, when we used 71 trapezoids. And we want to see how this compares to how the Romberg's method compares if I simply use the trapezoid rule without the Romberg's method. So first, we're going to start filling the table. We fill the table first. The first value, we use one interval for the whole domain. If we use one interval and we use the trapezoid rule, we fill the first number. The first number is 8.38906, and you can see when I compare 8.38906 to the true value, which is going to be closer to the 6.38948, it's actually highly inaccurate, as expected, of course. Using one interval with the trapezoid rule is not accurate. Then we divide h by 2, and we repeat, and then we get a number that's 6.1281. It's still not very accurate, but what we can do is if we take this value and that value and use the Richardson extrapolation or the Romberg's method, we multiply the first number by 4, this number by 4, and subtract this and then divide by 3. We're going to get 6.42, and you can see I'm already 6.42. I'm already getting closer to the 6.38948. We will repeat. So this is the table. We already know 6.42 is not that accurate. We'll just repeat and see how accurate it's going to become. So we will repeat by filling the next the 3 cells that you can see in the table in front of you. So we're going to divide this last h by 2. So we're using a trapezoid of width of 0.5, and when we repeat, we get a number of 6.52. Then to fill this cell, we basically take this number, multiply it by 4, minus this number divided by 3. We'll get this number, and then we fill the next cell. The next cell is filled by multiplying this number by 16 minus this number divided by 15. And we're already getting a very accurate number. So we're getting 6.38924, which is already very accurate, even though we only used the trapezoid of width 0.5. But we used all the information here with some mathematical manipulation to obtain this very good estimate. We can see that this estimate, which is 6.38924, is already very close to the true value, and the error is actually less than the 0.00042. So let's see how many trapezoids or how many computations did we use. So here we had, when we used h is equal to 2, we had 1 trapezoid. Then we here had 2 trapezoids, and then here we had 4 trapezoids. So you can think of it as 4, 5, 6, 7 trapezoids versus 71 trapezoids when we did the trapezoid rule without any extrapolation. And so you can see this method would be much faster if I use it to, it's actually would be much faster than the trapezoid rule alone. All right, we're going to give another example. Here is a function that I'd like to integrate from 0 to 1.5 using the trapezoid rule. We'd like to first use the trapezoid rule, define the number of intervals, the h and the trapezoid rule, and the true value and the error. And then after that, we'd like to use the Romberg table with depth k equal 5 and then compare the accuracy. And as expected, of course, that we're going to find that the Romberg table will produce very high accuracy without having to go to need very high number of trapezoids. All right. So when we use n is equal to 1, 2, 4, 8, 16, 32, 64, 128, these are the number of trapezoids, and this is the corresponding width of each trapezoid. You can see this is the value of the numerical approximation. This is the true value, doesn't change, and this is the difference between the true value and the trapezoid, the value from the numerical method. And you can see the numbers decreasing, and depending on what level of error you're looking for, you can choose the number needed. Now, what I want you to look at is the error produced after 128 trapezoids. We're getting an error of 0.0001. Now, what I want you to see is that later we're going to use the only up to the 16 using the Romberg's method, and we're going to see that with 16 trapezoids versus 128, with 16 trapezoids, we will be able to obtain a similar, even smaller error using this Romberg's method. So, with Romberg's method, this is the table obtained with the Romberg method as we explained in the previous example. And this is the difference, this is the table showing the difference between the true value and the approximation. And you can see that we're already getting very, very high accuracy with this table. Now let's remember how we formed this table. This, we used n is equal to 1, 2, 4, 8, and 16. Because this is, we used h for the whole, one trapezoid for the whole one trapezoid for the whole domain, and then divided h by 2 and so on. So you can see we obtained this very, very high accuracy with only up to 16 divisions. So we only used the top part in this table to obtain very high accuracy. Now I want you to compare this number, which is the accuracy if I simply use 16 trapezoids, for this number if I use 16 trapezoids, but I use all this previous information to generate the Romberg's table, which can then be used to give me this number, which is very accurate in comparison to, or much more accurate in comparison to just this number straight from the using the trapezoid rule. So, using the Romberg's method, extrapolation was used to reduce the error without increasing the number of trapezoids.